Okay, it's 10:30. So welcome everyone to the next session. My name is Jeff Essick, and I'm a librarian at NC State. I'll be the host for this session. We've got a really good topic for you today. The topic is artificial intelligence, using artificial intelligence to find water meter box locations. And our speakers are Shannon Martell, Catherine Browning, and Wendy Keys. And you can see Shannon is with the Charlotte Water, and Catherine and Wendy are from ESRI. So we have a chat box on the left of your screen that I welcome you to submit questions or comments that you may have as we go along, and then we'll have a few minutes at the end that I will ask those questions, and we'll see what they say. So without further ado, go ahead and begin, Shannon, and thank you very much for being part of this.
Thank you. Good morning, everyone. I'm going to go ahead and just stop my video during the presentation. Let's see here. All right. As Jeff said, my name is Shannon Martell. I work for the City of Charlotte. I serve as the GIS manager for the Charlotte Water Division. With me is Catherine Browning, an ESRI technical advisor, and Wendy Keys, an ESRI data analytics consultant. Today, we're going to discuss the use of artificial intelligence to find water meters. And there we go. All right, here are some quick figures about Charlotte Water. Charlotte Water is the largest water and wastewater utility in the Carolinas. We serve more than 1 million customers in the city of Charlotte and in surrounding areas. On an average day, we pump 106 million gallons of drinking water, treat 78 million gallons of wastewater. We have over 8,800 miles of pipe, 17,000 hydrants, and close to 300,000 water meters. All right, so how did this project get started? Well, the ESRI Charlotte office came to the city of Charlotte and did a presentation for the entire GIS staff across the city. They were discussing, some new software updates and some projects that were going on in the area. And one was how the city of Raleigh was using artificial intelligence to find pavement cracking using imagery. They were mounting the cameras in their, I guess, their solid waste trucks. And I just asked if the same process of using imagery could be used to find water meters. So why is AI a good option for Charlotte Water? Well, water meters are arguably our most important feature class, but 70% of our meters have not been field verified. We've either used engineering as-built, aerial photography, we'll use Google Street View, or sometimes we just end up kind of just, in some areas we just put a dot on the lot somewhere. We also spend hundreds of thousands of dollars a year on dedicated survey contracts to locate water meters. These are both for residential and commercial water meters. And then we also found out that customer service was using a text field in their software, giving written descriptions on meter locations, and we definitely wanted to see if we could improve on that. So to start this project, we decided to use credits from our ESRI Advantage program. Catherine's going to discuss a little bit for you on the next slide, but we purchased this in October of 2017. It is a departmental Advantage program. It is separate from the citywide Advantage program. Charlotte Water was assigned an ESRI technical advisor with a background in local government water utilities.
So I just wanted to let everyone know that we're having rolling blackouts in Dallas, where I'm based. And so if suddenly I disappear, it's not that I don't want to be here, but I could lose connectivity. So I just wanted to mention about the ESRI Advantage program. It is our most popular professional services engagement. We have hundreds of them all over the world. And as part of the program, you get your technical advisor who's really knowledgeable on your industry. My background, I have over 25 years in the water industry, over 22 years in GIS, and I also have an IT background, over 30 years in IT. So prior to coming to ESRI, about 9 years ago, I actually was a database manager at Anchorage Water Wastewater Utility up in Anchorage, Alaska. And oh, by the way, this week, Dallas has been colder than Anchorage. So as part of this program, we all work as a team. I will bring in experts like Wendy Keys, who's on our data science team, and to do analytics if that's the appropriate expertise that we need. And I work with the account manager, I work with the solution engineers. We all form this team to help our clients kind of realize their goals. And Shannon's been kind of our creative genius. She always comes up with great ideas. And so one of the things that I did was I kind of worked to find out who would be the best resource to kind of do a proof of concept. So if you could go to the next slide, Shannon. So what we wanted to do is we wanted to test out the technology without putting in a lot of effort as far as hours in their program. So we wanted to see if we could reach out to the product team to see if they would help us do a proof of concept to see if the technology was such that we could really leverage it in a more extensive activity. And we did find that it was really accurate. So back to you, Shannon.
Sure. So our proof of concept is we purchased a GoPro 7 Black and a vehicle mount. We drove around and collected about 1,000 images of meter box locations, and we were looking for ones in various locations like grass or concrete or asphalt. We then uploaded those to ESRI, and ESRI used them to create and train the model. On this next slide, this is actually the background image. It's one of the training images from the GoPro, and you can see where we labeled on the image where a water meter box was. And we went through this process, and ESRI was able to train the model to find the meter boxes. We ended up with a mean intersection over union of 0.9982. So mean intersection over union is used to measure the accuracy of object detection and imagery. And so if you look at the image of the stop sign, the green box is called the ground truth bounding box, and this is the box that's drawn around the object by a person. The red box is the predicted bounding box, which is drawn by the computer. So you want those two boxes to be as close to similar as possible over what you're trying to detect. So the calculation is a ratio, and the numerator is the area of overlap between the two boxes, and the denominator is the area of union between the two boxes. So a perfect score would be a 1. So using the graphics across the bottom, a poor score would be a 0.4 ratio, a good would be a 0.7, and excellent is 0.9. So with us having a 0.9982, I mean, that's a really great score. If you're interested in this mean intersection over union calculation for object detection, I have included the hyperlink to the website where I've got all this, these images from for the slide. And then here, Catherine, if you want to discuss a little bit about the results.
Sure. So again, we worked with the product team, and they were able to kind of take images, and they were able to train the model. They would come up with a prediction. We would do some ground truthing. And again, it was incredibly accurate. Now, I'm just a facilitator as far as this project goes. This is not my area of expertise. So I'm now going to turn it over to the brains behind the project, and that's Wendy Keys, who has a PhD in economics, and she is our data analyst guru. So over to you, Wendy.
Thank you. Basically what we did is we take these images and we start out with labeling, and labeling is essentially drawing pictures or drawing polygons onto an image so that we can teach the computer what the thing we're looking for looks like. And so we give it lots of examples. And do we want to advance to the stack, or
Sure.
just to talk about the process? So we take this raw imagery and we run it through a model. So we take lots of examples so that we can teach the computer by giving it lots of examples of what something's supposed to look like. And it goes through a process of what I call the hot and cold game, where it assigns weights. And so it takes these guesses at what it finds in the image, and based on the accuracy of those guesses, it goes back and adjusts those weights until it gets better and better. And so I call it the hot and cold game, because as it learns, or the way that it learns is by by seeing how much closer to the ground truth it's getting. And the closer it gets, the better it knows of how to adjust those weights. And it starts to learn what things are distinguishing that that makes something what it is, that makes a water meter box and not a piece of sidewalk or curb or mailbox or the other things that might be in the background. Should we go ahead to the next slide? Or I don't know if you wanted to talk about some of the stuff on that slide, Catherine.
No, I think we're good.
Okay. So what we're going to be doing, we've got the proof of concept finished. And so the proof of concept was very promising. We had very good results. And so that inspired us to go ahead and go to the next level. And so the next level is going to involve not only collecting a lot more images, so we want to collect a lot more in different contexts. So we've got some in residential areas, some in commercial areas, some in industrial areas, so that we can teach the computer these different contexts and what different meter boxes might look like. But we're not only teaching the computer now to find them in the image, we're also going to be applying photogrammetry in this next phase so that we can locate where on the earth those meters are. So it's not just enough to be able to find it in the image and say, this looks like a meter, but we want to be able to pinpoint the lat long of where that meter is located. And so I think Shannon is going to talk about the change in equipment that we're going to be using to accomplish that.
Thanks, Wendy. All right, so the major result of our proof of concept was that we felt the GoPro camera was not a good fit for the project. The image quality was really good, but the accuracy, because GoPro does collect some locational information, it just wasn't very good. It could be as much as 30 feet off, and with Charlotte's higher density development, this really wouldn't improve our accuracy. We also found we have a lot of on-street parking, and the GoPro just facing one direction, it was kind of limiting on what you could find in the images. Also, the GoPro takes images based on time. So we had the camera set to take a picture every 2 seconds. So this meant on higher speed roads, we were getting less images of the meters, or the driver was going to have to drive slower, which we really didn't feel was safe with traffic. So we went out to look to see what other kind of cameras were available, and we ended up selecting the Trimble MX7 camera. This is a 360-degree camera. It has 6 cameras in the device. There are 5 that wrap around to make the circle, and then there's actually a 6th one that points up. It does post-processing, have an accuracy of about 2 inches. The capture rate is based on distance and not time, so this takes out the issue of speed limits. It also comes with software that allows you to import driving routes, and we use software called Route Smart to create our meter reading routes. So we were thinking we could import those routes into the Trimble software. So I'm going to discuss a little bit more about the MX7 image collection and the model training where we are right now. So we did receive the camera. It was early fall. It was shipped in several pieces, but it really wasn't complicated to assemble on the truck. We did buy some extra pieces that came with the camera to help improve accuracy. One was a small GPS unit, and then the other is called a DMI, and the DMI actually hooks to the tire of the vehicle, so it helps with the distance calculation, or your movement up and down the street. It is very specific to the rim or hubcap of your vehicle. So we had to measure the distance of our lug nuts to the center, and it also does require you to drill a hole in your front fender. So it's not something that you can move from vehicle to vehicle. You basically need to pick one vehicle and use that one. It's also, if you move it, you also have to recalibrate it. We are coordinating with City Fleet to see if we can use one of their facilities to store the vehicle with the camera mounted on it when we start running every day, just because it is kind of heavy, and trying to put it on this taller truck is a little bit tough. And also, we were provided training from Trimble for 2 employees, and we did it all over like WebEx meetings. They really helped us get it set up and calibrated, learning how to import routes and driving routes. So we selected 10 areas in the city of Charlotte It was approximately 1,299 meters, and these meters had already been surveyed, so that way we could test the accuracy of the camera against meters that had already been surveyed. We also used our Route Smart to create the driving routes, and we imported that into the Trimble software. The top image, you can actually see this is a picture of the software in the truck. And you can see the 6 camera images. You can see what they're seeing as you're driving, and you can see yourself actually on the map. So the next step was to take these images from the MX7 camera and label the meters to train the model. And like Wendy said, labeling is basically how you treat them or train the model to find what you're looking for. We did end up breaking these labels down into different meter lid types. So we used concrete, white epoxy, green epoxy, metal hinge doors, metal plate, and manifold. I did include, let's see if I can get the animation to work. Yes. This is a screenshot of the software that we use. It's called CVAT, or Computer Vision Annotation Tool. And this is actually an image of the MX7 camera's image. Because it is a 360 degree image, when you flatten it out, it does come distorted. So if you look across the bottom, you can kind of see those 5 scallops. That's the 5 images seamed together. And then you can kind of see where the camera points to the sky. So when you first look at this image, it looks like you're looking at an intersection, but you're actually just driving up one street. So if going from left to right, the left side of the image, you're actually looking up the street on the passenger side. As you look to the middle, you're actually looking now to the back. So you're looking over the back of the truck. And if you keep going the far right, you're actually seeing the side of the street from the driver's side. So it kind of ended up splitting it kind of in the middle of the street. So it takes you a bit to orient yourself, and you can actually see in this image the yellow box. That is where I have a labeled yellow. With the yellow is a white epoxy meter lid. There are 6 of us working through all the images. And it's taken us a couple weeks. We do have several thousand to work through. There's not a meter on every image. Like in residential areas, the density of meters will be higher on the images, whereas in more industrial commercial meter areas, you'll have more of the commercial meters, and they tend to be farther apart. So I wanted to give some examples of the images coming out of the MX7, some of the good examples and bad examples of what we found so far. And these are just a clip of a section of the image. So the first one, this is a white meter box lid, white epoxy, and you can really see it nicely. Here's another one where we've got 2 meters together. And then we found that leaves were actually a problem. So the meter in this image is actually in the middle bottom, and it's completely covered in leaves. So we did not label this image because we didn't want to confuse the model with looking at leaves or looking for leaves. And then this is another one. We know there's a meter there. I actually had to use kind of Google Street View to see where it was supposed to be in this image. And you can kind of see the blue paint on the sidewalk where they've done some locate work, but the meter is under the leaves and the sticks. So we're hoping that we can run this process annually, so that maybe like next year this meter will be uncovered, or if there are changes to the system, like meters have been moved or if they've been buried, we can look and flag those that are different than the prior area or prior drive. So some of the outcomes of using the MX7 camera so far, we did find that we were having to put 2 people in the vehicle to run the camera. One person was driving. The MX7 Trimble software does come where you can import the route, but it's just a visual route on the map. And we just felt that it was difficult to try to drive and look at the map to see where you're supposed to turn next. So the second person was actually just in the vehicle to say, turn left, turn right. And we didn't feel like that was very efficient. And with COVID, we really didn't want 2 people in the car together all the time. So we went out and purchased a subscription to a few licenses of Navigator. So right now we're working on importing what segments we want to drive for those days into Navigator and using that on cell phones to give verbal turn-by-turn directions so that we can get this down to 1 person in the vehicle. Also found in some areas, especially with the commercial meters with the metal doors. The images on the other side of the street tended to be a little bit grainy. So some areas we might have to drive both sides of the street. We tried compensating for this and driving down the middle of the road on, side streets, but we found that the meter was getting cut off by the top of the truck and the camera, so that didn't work either. A few other things, you can't run the camera in the rain. The rain gets on the camera lenses and kind of makes a mess out of your images. We did need to buy a server. We bought a 40 terabyte server to store the images. Early results, we're finding that we can collect approximately 4,000 meters a day, and then the images take about 70 to 80 gig worth of storage space. We're also having to go to the office to upload the images from the camera to the server. It was just trying to push that much data across the VPN it was really slow, and they weren't real happy with us doing that. So, and we're also doing the processing. We're remoting into a computer at work to do the processing of the images, just to put that all on the VPN. So the current status and next steps, we are finishing up labeling our images. We should be finished today. Like I said, there was about 6 of us working through all the images. We will then take all those labels and send them to Wendy. And if I get this wrong, Wendy, let me know. She will then take these labels to further train the model. We'll rerun the model with the new trained images and kind of review the results. We're going to continue working with Navigator to kind of plan out our routes, and we're finding that Navigator is having a little issue with uploading 4,000 points to it, so we're just kind of working through a couple processes to make that run a little bit better. And then we're also working on streamlining the image upload process to ESRI, because Wendy will be doing all the processing of the images on their servers. So I think we're looking at it's like WinSCP or some Python scripting to try to run that upload process in the evenings. Did I get that right, Wendy, on the training?
Yes, yes.
Okay, great. All right. So this, I just have myself and Catherine's contact information. If you think of something after the session you'd like to ask, please let us know. And unless Catherine or Wendy, you have anything else to add, this is the end of the presentation.
No, that was good. Thanks.
Yeah, thank you. That was so fascinating. I really enjoyed seeing about this project. We do have some questions. So let me see here. We've got one question. How many labeled images were needed to train the model so successfully?
Wendy?
So I didn't do the proof of concept. That was on our pre-sales side. I want to say, Shannon, you might know better than I do. Did you say it was about 1,000 images?
I thought it was around 1,300.
Yeah, somewhere in that range.
Yeah, I think it was about 1,300. We went out, we did the initial bunch, and then they asked for a few more. We went out and drove some more and uploaded those. So yeah, I think it was around 1,300 images in the proof of concept.
And we spent less than 40 hours on it too. I mean, it was probably around 33 or so hours of a consultant's time. So it wasn't a heavy lift. It was just to prove if it was viable. And then we brought in the big guns with Wendy.
Okay, great. All right. Was there a breakdown? Oh, excuse me, I'm jumping ahead. What percentage of the meter needs to be displayed for the camera recognition to occur? And along with that, was there a breakdown for how efficient each type of meter recognition was?
So for the first question, we're using a segmentation model. So in machine learning, specifically deep learning with imagery, there are 2 broad kinds of approaches. And so one is object detection, where you're trying to teach it to find different instances like stop signs or vehicles or pedestrians. And then there's segmentation, where we're asking the machine to classify the pixels in an image. And since we're using the image segmentation approach, we basically need to teach the computer what pixels look like when they are capturing, in this case, a water meter. And so the computer is going to learn from the color of the pixels, the density of the pixels, what kinds of other pixels are nearby. So it's going to be looking at arrangements and clusterings and color and a number of things. So what's important when we're trying to teach the computer, and this is something I spent a bit of time with Shannon's team in teaching them how to label, is that when you've got something in an image that you're trying to train the computer to recognize, you need to have all of it that is visible in the image. So for example, in some of those images, there are, you can see part of the meter, and then part of it is covered by something like leaves or overgrowth of vegetation. And so we draw a polygon around the portion that's visible so that the computer doesn't get confused and think that leaves are water meters. So it's really important to make sure that you capture any part of it that's visible for a segmentation model. And what was the second part of that question?
Was there a breakdown for how efficient each type of the meter recognition was?
Not in the proof of concept, because that was just proving out whether it was viable to move forward. But we will be doing lots of very, different kinds of validation tests and seeing which of the meters the model is better at picking.
One thing I will mention for the proof of concept is because we had a lot more images of meters in grass, it was more accurate picking those up and less accurate. Was it grass, Shannon, that was more accurate, or was it cement that was more accurate?
I think it was the grass, because we just had the most examples of grass.
But that wasn't so much the model as it was how many images we were feeding into it. And again, because it was a proof of concept, the purpose of it was to determine how viable it was. And then we were able to bring in Wendy, where we could really get to a lot more detail and do the segmentation analysis. Is there another question?
Yeah, I've still got, looks like 3 more questions. So the next one, where is CVAT being run for annotating the imagery? Is it on premises or in the cloud?
Oh, go ahead, Shannon.
Sorry. We ended up setting it up on site at Charlotte. Catherine and I forgot the other gentleman's name helped us configure it, but basically we just picked one machine and set it up with an admin, and then we added the users for all the reviewers.
I think it was David Yu who helped.
Thank you.
Okay. And did you end up having to merge training classes iteratively as you went?
You mean for training the where everybody was drawing in the polygons for labeling? If that's the question.
I'm not sure. I'm just, I'm just reading it. Did you end up having to merge training classes iteratively as you went? Maybe they'll clarify.
We had different groups of training. We had different groups of training. So, but we had an initial training class, and then I think there were several others training after you guys had gone out, and Wendy was able to look at the data. Correct, Wendy? Wasn't there?
So I think in the proof of concept model, I don't think there was a distinction between different types of meter boxes. As we look forward and thinking about the different contexts and the different ways that meter boxes can look, we identified, how many was it, like 6 or 7 different distinct meter coverings. And so just in reviewing the images before we started labeling, we identified and I worked with Shannon's team to, with their subject matter expertise, to identify the different kinds of meters. So what might meters look like, so that we can effectively train the computer to recognize them. And knowing that there are, some really distinct, both in terms of color and in terms of shape and in terms of the texture, we wanted to make sure that the machine would get really good at it. And so it was, it's in this second phase that we added different classes. so that it's not just finding a meter, but it's specifying which kind of meter it's finding.
Okay. I'm going to keep asking questions. We are at time, but we've got a break. So I'm just going to keep, if y'all don't mind, if
I'm
you're
good
willing
with
to
it.
Yeah.
stay. Okay. Because we've got 3 or 4 more that have come in. And I'll make sure I'm not skipping. So what is the estimated total outlay in terms of, I just lost the chat window. It just, I didn't realize that was going to happen. Are you still there?
Yeah, I'm still
Yes.
here.
Okay, I don't know if people are still able to connect or not, but there was a question about the cost.
We spent, well, I can't answer about the camera. Shannon can do that, but we've actually allocated about 120 hours for this, deeper dive into the technology. We may or may not utilize it all. One of the things about the Advantage program is, if you don't use all the credits, then we close down the activity and those credits get released back into the Advantage program's pool of credits. And so it's 2 hours of consulting for each credit. So we set it up for 60 credits.
Okay, that makes sense.
And Shannon, for the camera, can you say the approximate cost or?
The camera with all the software and the added pieces was about 90,000.
But the return on investment was first year because of how expensive the surveys were every summer.
Yeah.
Okay.
Yeah, because one thing we did consider when at least when I came on is I asked Shannon, why do this instead of sending interns out with field collector to to walk the routes and do that. And we found that this was much more cost effective and timely than a more manual method.
Well, thank you so much. Again, I apologize. The all of my chats just disappeared, so I don't know the remaining questions that people asked. I think we had answered most of them. I did have a number of people who expressed that they thought this was a very just an amazing presentation, and they were very impressed with your work, and so I was going to also read those, but there were a lot of accolades for your talk today and for the work that you've done. So thank you again very much for presenting. And if I'm sure if people have further questions, you'll be glad to, if they can get in touch with you directly, you'll be glad to help them with that.
Sure.
Yes,
Sure.
absolutely.
So.
And we're always willing to bring in Wendy. So Wendy has a whole team that works with her too.
So Catherine, if someone has questions about the ESRI Advantage program, are you the best person for them to reach out to about that?
Sure,
To get
sure.
started? Okay.
And then if I need to bring in someone else, I will. So.
Yeah, that sounds like a great resource. All right. Thanks again, everyone. Thank you for joining.
Thank
Thank
you.
you for your time.
All righty.
Bye-bye.
Bye.